Okay, I become the first person to give presentation today. Hello everyone. My name is Jingyu Yang. I'm the first year graduate student of AME department working with experimental combustion. Yes, that's right, I'm an experimental people, and the majority of my previous research and ongoing job are related to experiment instead of computation. So this class is the most challenging class I've ever taken, but I'm very interested in that, and we definitely know a lot, although sometimes we are undertake mountain peak with pressure. And for my project, I just select a kind of easy topic, which I want to apply what we've learned in class to a real-world case, which is using the Bayesian network approaches to predict the wildfire consequence. So wildfire, when it happens, that will definitely generate some damage and lead to some cost. If you are a person working in maybe a government department, when there's a wildfire, you will be probably surrounded by a lot of people from different media keep asking you annoying questions about the consequence of the wildfire. So if you want to do good job, you have to give them some results of the consequence of the wildfire. However, to evaluate the consequence of the wildfire is a kind of hard job, since it covers information from many different areas. For example, you have to think about the type of your city and the road density and your type of your construction. It's a kind of knowledge from civil engineering. And the landscape, environment, something related to geology or biology, and the value of your building is definitely a job of business school. So in a word, it's complex and hard. It gives a nightmare to the traditional methods to calculate the consequence. However, the Bayesian network or HERO can handle the information from different areas very well at the same time. And there are many researchers using Bayesian network to do some work on different areas. For example, in biology system and on the wildfire. And this person, whose name is Papa Costa, I don't know his name, the correct pronunciation of his name. He developed a Bayesian network and used that to assess the building damage caused by wildfire in Cyprus. And in his work, he just used commercial software named Hygiene. It's a very strong software. You can actually draw your Bayesian network, and that's the input your CPT and click run, and you will get your result. That's very simple. But I'm very interested in his job and want to reproduce his work, do a similar work, but I don't want to use commercial software. And I want to use that. I want to build a Bayesian network in MATLAB and select several inference engines and try to see what I can get. So first, let's decide our aim. The Cyprus is an island in Mediterranean Sea, and it's very large, and it's very hard for you to study the whole island at the same time. And so the author, and similar in my work, we just separate this island into thousands of little cells, and each time we just focus on one cell, which is represented by the right square in the map. And it has area of 1 kilometer square. Now we decided our aim, the cells. And the next step is try to figure out one way to quantify all the consequences of wildfire. Several researchers has established these functions, and gave that a good way to formulate the expected value of the wildfire is this function, and this one left-hand side is expected value, maybe the little value, and it's a function of probability of hazard and probability of damage conditional on hazard, and here's the cost functions. And so once we know this formula, we got some hint to consider the indicator, to consider the way to calculate our consequence. The next step is try to find indicators represent hazard, the damage, etc. Let's come back to the little cells again, and our job our ongoing job is to find the indicators. Even if in the little cell there's still a lot of indicators you have to think about. For example, we assume that the hazard should be the burn area and the fire intensity, and there are several, and there something influence your damage. Maybe, for example, your building type, if it's it is apartment or it's a single building, and the how many buildings in this location, the building density, and at the same time, your distance to the fire station and the road surround you maybe also play a role inside, because that decides your chance to get help from fire department. If you have a better chance to control the wildfire to fire, that will definitely reduce your cost. So this figure just give us some hint about how to build the graphic model. So after we figure out what indicator we want to study, we can create this graphic model like this. And to be honest, several indicators has been ignored since we only want to study something we are really interested, and it's really hard for you to study everything to build everything in a model. And on the top, the violet nodes represent the hazard, which is the burn area and fire intensity. These light green nodes represent the item at risk. We call it explorer. This nodes will influence your damage of your building and influence the damage cost. So once we get to our model, the next step is to find the conditional probability distribution, and here we do another assumption that we assume each node has finite states, and we also assume that the node follows discrete distribution instead of Gaussian or other distribution. In the paper, the author just gets this probability distribution value from some literature research, government report, or historical record, just like the map shows there. However, unfortunately, those data, I know it's very important, but this data were not given in the paper. That gave me a nightmare to continue. So, and forced us to do some simplification and do some assumptions and try to fix this hole. Here, let's come back to the graphic model again. And since now we have to do everything ourselves, first I want to do some simplification for this graphic model. If you, for example, when you decide the probability for the building damage, you can see that it has 4 parents, 1, 2, 3, 4, and each parent has different states, which means that if you want to create a table that will be a really huge, large table, you have to input a lot of data, and you are under high risks to make mistakes. And actually, I made that. And but interestingly, if you go to his paper and check that the building stock and the construction type has almost similar meanings. So to simplify this model, I just combine them together, and then assume that the right node have 3 states inside, and the yellow node has 2 states inside. So that's fair enough, but not give me a nightmare to decide the CPT. And also there's an independent assumption to simplify our chain rule. So okay, let's give me, here's a very simple example for CPT for this node. This is a fire suppression, and it has 3 parents. And fire intensity, this parent I define it as 3 states, and this 2 has 2 states inside. So you can build this table. You can build this table and consider different states of different parents, and each element in the table I just give a reasonable guess for the probability. The meaning of reasonable is that, for example, if you have a really low fire intensity and your building is very close to the fire station, and you are surrounded by a really advanced road system, which means the road density is very high, you will get better help from the fire department, which means that the fire control could be successful or medium instead of poor. So, for example, this case, I just gave the poor states as a really low, gave him a really low probability, and gave the medium control and successful control a really high probability. So now we built our graphic model, and also have our probability distribution table for each node. The next step in MATLAB is to call the inference engine. Here in this problem, we tried 3. The first one is the junction tree inference engine, and another one is loopy belief propagation engine. We have talked a lot in the class and practiced a lot in the homework, so I won't discuss this too much there. And there's another a little bit extension to use a sampling engine called the likelihood weighting sampling engine, inference engine. It's a kind of sampling engine. The basic idea of sampling engine is that you just take a sample from your Bayesian network, and compute the probability of this sample. And then keep sampling that. If you get enough sample, the final distribution of your sampling would be close to the true distribution. That's the basic idea of sampling. And likelihood weighting sampling is a little bit updated sampling work. It's just we have the evidence, and it fixes the evidence variable, and only sample the variables not related to the evidence. Only sample the non-evidence variables. And for each sample, we just multiply it by the weight we decide. There's a lot of literature talk about the likelihood weighting inference, and some of them are very complicated and contain a lot of information. Here I just briefly introduce that by using a simple examples. Let's come back the sprinkler model, which we are very familiar with. So, and assume that we are required to compute the probability of R, which is ring, given S is true, the sprinkler is true, and the white grass is true. And let's start our sampling. First, we should sample the C, the cloudy. There's no constraint on C. We just assume that we sample it as truth, which is plus C. And since this one is decided, when we next sample the S. So since this decide, we can only select our S from this right box. But however, the S is fixed by the evidence, which is true. So we can only select the value of 0.1. And then we got our first weight of 0.1. And then come to R. And since this simple, which is plus, so we can only select our values from this right box. But there's no constraint on R, which means that we can sample whatever we want. Let's assume that we sample R is true. R is true, and then we move to sample the W. And since RS is forced to be true, R is sampled to be true, and come back to the evidence, we first W to be true. So we got the W can be only the 0.99, and we got another weight. Finally, our total weight is 0.1 multiplied 0.99, which is 0.099, and we just multiply our sample. This is our sample by this weight, and then do a lot of iterations, do similar job, and finally get the result of the final probability and get this one. There is some problem of the likelihood weighting. For example, if you are required to compute probability of C given S and R, your value you get maybe sometimes doesn't go well with the evidence. Since you see you start sample the C here, you don't need to think about the S and your evidence, which is S and W. So yeah, there's some update for the sampling. There's some other sampling engines to fix this problem, which I won't talk here. Here's the result I got from the MATLAB, and this plot on the left-hand side, I just fixed the burn area to be 0 to 0.01 kilometer square, and changing the fire intensity. There's a dropping trend for the cost. That's because I assume that the higher fire intensity has a really low probabilities. And this plot on the right-hand side, I just fixed the fire intensity to be this one, and changing the burned area. This shows generally shows increasing trend as a function of burn area. That makes sense, since if you have same fire intensity and have a larger burn area, your result would be a little, your cost will be a little bit large. And this plot also shows something for different inference engines, as we know that junction tree is a kind of accurate engine, and the belief propagation and likelihood weighting approximate engines. You can see that for this case, the junction tree works very well with compared to the the belief propagation works very well, and there's some difference between the likelihood to the junction tree, and this one belief propagation works also very well, but except there. Okay, if you do the similar work for all the thousands of cells on the island, you can end up with this damage cost map. I didn't do that in the project, since the author just separates this island into 9,000 little cells, so I don't have enough time to do everything for the whole island. So this one just gives you a hint about the final result we can get. And there are some other things we can talk, and the quality of sampling as a function of number of your sample. So you can see that the likelihood weighting inference engines results come close to the junction trees result. The difference is the probability difference means the difference between junction tree and the likelihood weighting. So if you increase your number of sampling, you will reduce the difference, which means that the likelihood is close to the junction tree. However, there's no free lunch, and if you increase your number of sampling, that definitely increase your time take. Okay, future work, definitely for the field work of this wildfire study, you can definitely add more information, more source, more nodes, and each node you can separate into more states. That will definitely increase your accuracy of your approximation. And I also think about for my own research, I also think about one way I can maybe I can apply what I've learned in this class in my research to do some uncertainty quantification for my experiments. That would be interesting. To conclude today's presentation, first is very simple project. It's a simple topic compared to you guys. Maybe Bayesian networks definitely a really strong tool which you can use to evaluate the wildfire consequence. And I'm also thinking about one way to apply it to my own research. And the advantage of Bayesian network is its ability to cover information from different areas, but it's still very computational expensive. If you build a really large Bayesian network and you need to do a lot of work to find the CPT. And since the CPTs are known it didn't given in the paper, we can now compute our results with the author's paid result. And another two junction trees are exact approach, and another two approximate approaches, and that's it. Thanks. Yeah. Yeah. So he asked me where's the most computational expensive parts in the junction tree to compute. I think that I don't know, I'm not sure exactly. I think my answer is that maybe in the junction tree, you have to, when you run the code, you have to find the optimize the best junction tree for the algorithm for your model. So maybe that maybe costs some time or makes it computationally expensive. I didn't do that deeply here. Okay, sorry.
I'm Zhang, a second-year PhD student in electrical engineering. I'm majoring in image processing. And today I'll introduce you my term project, linear time algorithm in Bayesian image denoising based on Gaussian Markov random field. And we see this familiar graph here. It's what I did. I have observation of several degraded images, which are noisy, and I hope to infer what's the original clear image is. And for Bayesian image denoising, I mainly have two steps. First is the hyperparameter estimation by EM method. It is we are really familiar with. It is expectation maximization. And second step will be the image restoration by MAP, maximize a posterior method. And in this grid, we have n pixels here, and both these two steps requires an inverse of n by n covariance matrix. Requires computation count will be the order of n cubed, and the latest algorithm make it order of n log n. And this paper achieved the linear time. That's the main computation of this paper. The reason why I took this paper because it's firstly highly related to what we have learned on the class, like GMRF, a Gaussian Markov random field, and the expectation maximization method. Both the framework and the method is what we are familiar on the class. And second reason is that it's highly related to what I'm doing here. I'm doing the multi-image alignment, and the multi-image denoising is the best way to show my algorithm itself. So I'm really interested to their method. The third reason is that their paper shows excellent clarity in both inference steps and parameter settings. It's very clear for me to follow each step, so I will not go into a loop or I don't know what's going on. I'll spend a million time on it. In this report, I will first introduce the framework of Bayesian image denoising. And second, I will introduce you their linear time algorithm. Second, I add a comparison algorithm to this paper. In previous paper, they only used the averaging method, which is just add images together and divide by the number of frames. So I think it's too simple. I hope to show more features of this algorithm. So I add the method called VBM3D. The original name is very long. It's a video-based denoising by sparsity 3D transform. It's very long, but we call it VBM3D. And this method shows very good results in many papers. So I want to show the comparison between the paper, the algorithm in this paper and the VBM3D. Last, I will show you the results and we can discuss the results. Given an original image composed of V by V pixel, a degraded image of the same size of the original one is generated by adding additive white Gaussian noise, AWGN, to the original one. Suppose we independently obtain k degraded images, and k is bigger than 1. We denoted the original image by the vector. So it's actually a matrix. We just vectorize into a vector to simplify the computation. And it has n pixels, so n entries in this vector. Similarly, we denote the case degraded image by the vector y. Next, I will introduce the definition of prior distribution. For V by V square grid graph, GVE, V represents the variables, the nodes in this graph, and E is the edge. So the prior distribution is defined as this one. So here we see this thing. So we know it's the undirected graph, right? and it's represented by the exponent of energy functions composed of the xi square, and the difference between numbers. Then the parameter b, lambda, and alpha is the hyperparameter we want to estimate. The partition function is written this way. We can also write them in a more compact way with this. This is the precision matrix. It's the reverse of the covariance matrix. And this big lambda here is the graph Laplacian. What is the graph Laplacian? In its diagonal, when I equals to j, it is the degree of nodes. Say node I. What's the degree of node I? It's how many nodes connected to node I. Its neighbor, the number of its neighbors. So in the else element, if it belongs to F, it will be the minus 1. Why we need to write it into this form? Because with this form, it will simplify the method, and we can compute the inverse of this precision matrix easily by matrix decomposition. And here is the model of noising. Since we use the AWGN, the additive white Gaussian noise. What is AWGN? It is AW additive. Additive means it is added to the original pixel. And the white Gaussian noise because refers to the zero mean, and the noise distribution is represented by its variance, sigma squared. And we can write it in this way. Now we are ready to define the posterior distribution. Also, since it's according to Bayesian theorem, it is proportional to the noise distribution and prior distribution. We define it in this way. Also, the undirected graph, and with the partition function like this. Now the hyperparameter become 4 elements, adding this sigma square noise variance. We can also write it into more compactly with this precision matrix here, with the graph Laplacian big lambda. Since we already have the prior distribution and posterior distribution, we can now to do the estimation of the hyperparameters by EM method. We can say the first step will be the Q function. Define the Q function. We need to maximize later. And it's in this way, the integral of the production of the posterior distribution and the joint distribution of mu1. And what is the joint probability? It's defined as the production of the noise distribution and the prior distribution. Next step, we will compute the partial derivative for each hyperparameter, which denoted as this gradient range. What we actually do is update each hyperparameters by gradient descent method. What is gradient descent method? Is here. Since we have some old hyperparameter plus some updating rate and with this gradient. However, this requires the inverse of the covariance matrix, make it the computation time is n cubed. For the image restoration step, we need to use the maximum of posterior estimation. According to the definition, it can be written as this way. This is to compute the x maximize the posterior distribution. Since the posterior distribution is Gaussian, we can write it in this way. It's the same as the mean of posterior distribution. And to simplify, it can be written as this way to compute. And because it includes the inverting operator for the precision matrix, the computational time is n cubed. Here, very smart people propose some really like mean field approximation and multi-belief propagation. They lead to a same linear equation here. What we actually do is update the mi from the hyperparameters and the old f, and the computation time is linear. So what to make the whole algorithm linear time, what we need to do is to deal with the partial derivatives in the EM method. What they use is the energy, the free energy of the prior and posterior distribution, written in this way. It's defined as the Manners log z. By using this free energy, the gradients can be rewritten as this way. And the next step, I will introduce to you how to make the computation of these partial derivatives in a more better way, with the computation is a linear time. And remember, this equation will be the equation star. For the prior free energy, according to the definition, we just write it into this way. And with the graph Laplacian with lambda and the inverse discrete cosine transform, it can be written as this. We know everything except for this one, the phi sub I. Phi sub I is the element in this vector. The vector is obtained by the row major order vectorization of the V by V matrix defined as this. It looks maybe, it's easy to compute because we know everything. And the computation is linear. And we know the derivatives. It can be written as this. And the computation time is linear. Similarly, for the posterior free energy, refers according to the definition, write it into this way. And we already know this part is the f, and we have know the linear method for this computation. And for the determinant of precision matrix as post, it is written as this way. And we have a very good form. Similarly, the derivative is linear. Collect this partial derivative to the partial derivative of Q function equation star here. We have this. The computation is linear. Actually, it's a very good method. It converges with less than 30 iterations. And here I will first show you its comparison. The patch-based VBM 3D method. It actually has very easy form. Here, the T set rate is the patch in the V small v image in the frequency domain. V from 0 to n minus 1. So in total, we have capital N image. And the Z equals to Z is the index for the reference image. We pick the one of the degraded frames as the reference. In most cases, just the first one. And here, in the first part, it's just the average of all the patches. And the second part is actually to attenuate the frequency coefficients that do not match the reference. And A is the shrinkage operator, like this. And C here is the constant. It's fixed constant. Actually, is the tensor. And the sigma square is the noise variance we estimated for each patch. E sub z is the difference between the patch of the reference and the current one. It's easy to compute. And here is the result. For the number of degraded noise image is 3, and the input noise variance is 30. Image size is 256 by 256. I show the result of ground truth, the clear one, the averaging one, patched VBM 3D, and the linear method. I show their results by PSNR, peak to noise ratio, and SSIM, structure similarity, and their computation time. Both the PSNR and SSIM, the bigger the better. The bigger the number, the more similar to the ground truth. You can see here, the winner is the linear time here, slightly better than the patched VBM 3D. I think you can see here, the image is a little bit blurry than the other one. The reason is that this method is actually a kind of modified Wildfire feature. The function of it is just to reduce the high frequency part of the image. What's the high frequency part? It's noise and the edge. So when we decrease the high frequency part, it decreases the noise and the edge. That's why it's a little bit blurry. But you can see in this black area, it's less noise point. And from the computation time, we find the winner is the average, but the result is not that good. So the linear time works better. Here is the result for bigger image size, 512 by 512. The winner becomes the VBM 3D with better PSNR and less time. Let me show you the even bigger image size. It's 1026 by 1026. The winner still did a patch of VBM 3D with less computation. Does that mean the linear time was beaten by larger image size? No. Actually, we need to also consider the image number k. With the I just plot the PSNR from the image number from 0 it's actually the 3 to the 13. And the image size is 256 by 256. The blue line is the linear method, red line is the VBM 3D. Blue line is the average. You can see here. All of 3 methods is increasing with the image number. However, after maybe 5 images, the VBM 3D is beaten. And blue line, the linear method, outperforms the other all the time. With more image number, they are very close to each other. But yeah, according to the bigger number, VBM 3D is beaten. I also tried the image size is bigger one, like 512 by 512. Same thing happened. Maybe the right line, the VBM 3D is good in the beginning, but it's not increasing that fast as the other 2 methods. So it eventually will be beaten by the both algorithm. Now we have the conclusion. This linear time method can restore the noisy image more successfully than average method all the time, in all cases. For larger size and a small amount of image, VBM 3D is a little better than the linear time. But for the larger amount of image, linear method outperforms the other method. And maybe I will prefer use this linear method rather than VBM 3D in my later research. Thank you. Any questions? your question is why the number of images matters. Let me say the equation here. So, like this one. Just because when we add, if you have a distribution, for example, the Gaussian, and they affected by the same noise. If you add them together, the variance of noise will decrease by sigma square, will be decreased into sigma square over n. So the more image you get, the less noise variance you have. So it's something like, yeah, they like add them together and the noise variance will decrease. So the computation time, what do you mean the computation time? It's difference between the method to method. For all of the methods, the computation time will increase with the number of images. But for the averaging, it's very small, always less than 1 second, because you didn't do that pixel by pixel. You just directly add them together. But for the other method, it really depends. Depends on the feature of the method. And I also tried some results here. I find with more image number, the linear method has less computation time than the VDMC. Any questions?
Hello everyone, my name is Xinfei Wei. I'm from Department of Aerospace and Mechanical Engineering. And this is my first time taking this course, this kind of course. It's very great challenge for me. And it's my pleasure to do my presentation about theory labeling using the thing I learned in the class. I do this because of it's very interesting and it's a popular course project. On the website, when we search this labeling, we can find there are a lot of examples. The most famous one is the Caltech 101. They label the airplanes or other objects in our daily life, like a chair or table or whatever you can see. Or recently, there's another image lab. They label this birds, and they can characterize a bird in the end. This is also the reason why we do this labeling, because if you want to know what this is, you first have to label it. You have a big picture, then we have to say where is the object. This is a primary step. When we search on Google, we can find some papers. They talk about this project, this kind of project. This is Markov random field, and we have these observations, and there's hidden variables behind the observations image. And for popular method, iterative conditional mode. This method, we have homework in homework 2. We do this. This is the beginning of this project. Then, based on this ICM, we can do a graph cut. And graph cut actually can be applied not only on this ICM, it can also apply it on the LVP and the other methods. Because the graph cut, basically, it can tune a lot of pixels, not only one pixels. And then the third method I will talk about is the loopy belief propagation. And it's the first step to test the message passing method. And an advanced method could be sequential tree weighted message passing, which is based on LVP. And when I talk about this method, I hope you can tell me where I'm wrong, because I'm very new to this method. First, ICM, we can see this equation in our homework. Yeah, this part is from the observed value. The total energy is the sum from the observation, and the neighbor, this is from the neighbor. The most important part is actually both important, and this neighbor will be actually we can tune this neighbor. The observation we cannot change because it is what we have. And by summarize these two parts, we have a total energy, and whether accept or not accept this pixel change is decided by the energy, whether it's decrease or increase. In the end, we will have lowest energy when we tune all the pixels, and we do a lot of iteratives. It can converge to some value, and it gives me a result of what this image should be. And also, I said, this is the weighting factor from the observation or from the neighbor. We can tune this part. If we increase from the observation, the image will be different. And then I will talk about the graph cut. Graph cut is, for this part, we tune, we swap those colors. It's like a scissor, we cut through this path, and whether we cut or not, it's also decided by the energy. If I embed this graph cut into the ICM, it just calculates the energy again. But it will be more computational cost because the number of neighbors is enlarged when I do this graph cut. And if I increase the size or the D, if I want to swap a lot of pixels, then the time will be very huge, and it may be not very good for some complicated application. But it's very effective, actually. In my study, I didn't apply this graph cut in BP or tree sequential BP. This is an example in one paper. They talk about those parts. It's maybe we run ICM. It's C. It shows minimization, but actually we use graph cut. We can make those parts more smooth or better. And BP is message. We need to select some way to pass the message in a hidden Markov model like this. If we pick this, actually there are a lot of ways we can pass the message this is actually, in my case, I did it similar to the sequence tree. I needed to decide how to accept or pass the messages, and I needed to actually decide the formation of the trees inside this map. And in my case, I just do left to right, then top, bottom, and like right to left, pass again. And when I change a color of the pixel, I needed to maximize this message. And in calculation, I do all summation because if we do a logarithm, it's the same. We want to find the maximized value. It's the same as summation. And what we want is to have a larger B here. And similar to the ICM, I have a weighting factor for the messages from the observation and from the neighbors, 4 neighbors in this case. This beta is from the neighbors. And sequential tree weighted message passing is similar, is advanced of belief propagation. This case we have a complicated map here. It may be more complicated than this, but we can decompose it into a lot of very simple trees. Then we summarize the messages from each tree. We get a total message, and this works very well. And there are a lot of things we can design here. First is how we decompose the trees and how we weight each tree. This will be very interesting. And in this case, in my coding, I just do this left, right, and right, left, top, bottom, 4 cases, and I weighted with ABCD 4 weight for the trees. And similarly, this beta and sigma are still there. They are from messages from the observation and from and this is I'm going to talk about I run these 2 images. One is from the Kata 101. This is the bird library, an angry bird. And I needed to first turn this color RGB image into a black-white case. I just use MATLAB to decide at which range it should be black and which range should be white. Then I first run the ICM. It looks very good. This is after ICM, and we see this still there black inside the white, surrounded by the white. Then I actually run merge. Write a small piece of code. I merge this part to make it smooth, and then I label this to the airplane. And the energy cost, the total energy is decreasing. And I didn't show which theta and beta I use here. I can actually use different values to show a different result. And this is using ICM around the bird, and this looks good. And graph card here. And here this part is not very good. And this is the belief propagation. The belief, the BI, this is BI is actually summarized all the pixels in the images, and it should be increased. Actually, around a few steps, it just converged. And this is the bird, and this is the message passing at a specific tree sequence, and I say difference. Because of my coding is only using these 2 images, then I just show this, it looks fine. Then I want to show, I can also show, if I run other images, First, this case is ICM. If I take another image, this is labeled other bird. It looks also very good for the ICM. And this is from and this is along the sequence tree. Also looks good. In this case, ITM seems not very good because those big noises are not removed at this part. We don't like to see those parts. I believe the sequence tree looks good. The sequence tree looks much better than that case. And also, this method, the sequence tree weighted message pattern method, is a very flexible method, I think. Look at those parameters. We can tune the weight of each tree. I have two here, and also the weight from the evidence and the weight from the neighbors. We can tune those. And if I tune this to like 6, and it's one way of the message passing is increasing, and this could be, I don't know whether this is bad or not, but this can lead to a further step. We can select a better parameter. This becomes a hyperparameter for those picture recognitions. And, if we make it very large, it's gonna be off, I guess. Yeah, this is actually very off, this part. This whole part is becoming the bird. Because I propagate, I think left to right, I increased up to 10, and this way of message passing is dominant. This image is the finally code from MATLAB itself. I think they did a very good coding this part. They can turn this to right, very good. Okay. The conclusion of my study in this project is first, SEM can really work because it's like a Python model. We just tune one by one. We can get some value and some results. And GraphCut is actually an algorithm that can be used in any of these parts. We can just swap a lot of pixels and to see whether the result is bad or not. But the cost is when we swap a lot, we need to think about the neighbor. It has to recalculate it, much more than you think it is. And this propagation actually is very effective. A few message passing, we can reach a very good result. And this sequencing tree weighted message passing is, I think, very good candidate for those message passing, because we can have a lot of parameters to tune and have a very good result for any imaging. These are my references, and thank you for your attention. Yeah. I don't know. I